Tonight's talk, Nature-Based Solutions for a Changing Climate, is presented by Beck Mordini, who is the Executive Director of Biodiversity for Livable Climate, an organization whose goal is to contribute to the planetary regeneration through research, education, collaboration, and action to restore essential global biodiversity. Beck has 20 years of nonprofit experience, including protecting the biodiversity of native plants at the Santa Barbara Botanic Garden and protecting undocumented workers from exploitation in Washington state. Her studies of international environmental law at Nairobi, Kenya, were her first exposure to the issues of desertification and the challenges to global action. While practicing law in Colorado, she and friends founded Climbing for Life, a technical rock climbing program for at-risk youth. Her career shifted to nonprofit management as a grant writer, development director, marketing and communications manager, community liaison, and executive director. Beck has been a Pachamama Project Drawdown workshop leader, of which the Alexandria Library was benefited from that, and worked on county community climate action plan and testified on behalf of solar reforms to the Board of Supervisors. She has degrees from the University of Virginia and the College of William and Mary, with coursework in sustainable agriculture and sustainable business from local colleges. Beck, thank you so much for joining us.
Well, thank you, Megan. I'm so happy to be here. I don't think I need to say more about my background. I am the executive director at Biodiversity for Livable Climate. It's a handful. We'll say Bio for Climate most of the time. I really like to thank Megan and the Alexandria Library for having me here. As Megan said, I first spoke with the Alexandria Library as presenting on Project Drawdown, which is Paul Hawkins' project, and there's a great book that goes with that. Alexandria's been a leader in environmental responsibility, not only through education, but I know you have great programs in Alexandria that really make a difference. I'm going to go ahead and do a screen share. So there are about 40 slides. So that's why we're not going to take questions along the way, because I was telling Megan, each slide could be a little class in itself, as there's so much that we could talk about. What I'm hoping to do today is just tap on some of the things I think are most interesting and kind of give you a framework that you might not have considered before. So I'm going to go ahead and get set up and screen share. Great. Hopefully everybody can see the intro slide there. So tonight's talk is nature-based solutions for a changing climate. There's a lot going on right now, particularly if you live in the DC area. And tonight I'd like to take a deep breath and put ourselves in a space of deep healing. And we're going to be talking about how restoring the natural systems that regulate our climate can work. Our organization, Biodiversity for Livable Climate, is dedicated to restoring ecosystems to reverse global warming. We are founded in 2013. Our founders are in Cambridge, but we are a global organization and with people from all around the world, and we are completely remote. That is how I, the executive director, am here in Alexandria. My home library is Sherwood in the Fairfax system, but a lot of our activities do center and start in the Cambridge, Massachusetts area. You can see we work through education, policy, and outreach, and have recently added some actual eco-restoration ourselves, which I'll tell you a little bit about later. Our four main platforms of how you can restore ecosystems are based on plants, hydrating the soil and the system, and direct cooling and protect. And these may or may not make sense by the end, but there's certainly can learn more about that on our website. Today, I really want to focus on the nature-based solutions. So our agenda is pretty simple. We'll talk about where we are, which is on a hot planet. We'll do a little bit of the science behind it. I do that because our organization is science-based, and also I don't like to tell people what they should think or believe. I want you to see what I'm seeing and be able to draw your own conclusions. And then we'll talk about some nature-based solutions, primarily to climate change and extreme weather, and end up with some action steps for you and some discussion. All right, first the bad news. What we've been doing isn't working. And you can see from this chart the number of days above the average. So it starts in the year 2000, it starts in 1990, and it goes, the red is 1.5 degrees above, the orange 1.25, and then the coral is about 1 degree above. And over time, this is where we are. We have had, in 2024, a record number of days, and we are at 1.5 degrees. So we missed our Paris goals. There's so much politicization around this issue. We know that data is being taken down from websites. It's kind of a crazy time around climate change. So the good news is data is still available. And I'll show you some good sources. And also what I noticed in this chart, we don't have to go back to the 1800s to reach our goals. I mean, look at the years 2000. That's good enough, right? Okay, depending on how old you are, that seems like a long time ago or not a long time ago. Doesn't seem like a long time ago to me. So the way we were living then was working, and let's look at what we could do. And also, when we discuss nature-based solutions, you're going to discover we don't have to wait for all the global governments to come together to make these solutions work. So I think those are all really hopeful ways to look at the situation. So the graphs, I went to pull some graphs from the NASA site, and indeed they were not available anymore. But the Copernicus program is from the European Union, and their graphs are all still up there. This is a live link. I'm not going to take you there, but you can see all kinds of different temperature, water, Arctic ice melt, carbon dioxide, daily Arctic sea ice, some really great information. The two graphs I did want to share with you, and I know they look a little fuzzy and they're a little small. This is, or maybe that's just my glasses, but I'm just going to walk you through them because they tell a little bit of a story. So this first one is a graph that we've all seen. It's the atmospheric concentration of carbon dioxide starting in 2005. And this line is just going straight up. That's a pretty steep curve. This is the end of what they call the hockey stick graph. You may have seen Al Gore use, where it's kind of steady, goes up a little bit, and then just takes this sharp curve at the top. If you take the very end of that, this is where we're at. So we're at 422.1 parts per million of carbon dioxide. If you're familiar with 350.org, that was our safe zone. We passed that about, there's 350 right there around 2011, 12. So yeah, that's how things aren't going. And the rate of increase was very high in 2023. Usually we're increasing at about, less than 1 degree per year. And we had an increase of 2.9 parts per million. Parts per million per year. So that's a little disconcerting. So what did we do to decrease carbon dioxide? We switched to natural gas. Natural gas is 90% methane, 70 to 90% methane. And here's the methane curve, starting also in 2005. And it's going along. These ups and downs are seasonal variations we'll talk a little bit about. And then takes a giant leap in 2008. Which is when fracking really became an energy priority in the US. And yeah, we reduced carbon dioxide, but we're increasing methane. Sometimes technology isn't the best answer. That's all I want to say. So let's see a little bit about I'm going to take a look at the CO2 parts per million chart in a little more detail. And the only reason I'm showing this is to give you this little up and down, right? Every year it goes up and it goes down. And if you've been following, if you've been following climate at all, you probably already know why that is, but it's not a secret. This is the seasonal variation. Every year, plants absorb carbon dioxide in the spring or summer, and not in the winter. This is a little short video that is from NASA, but it's on YouTube, so I think it will play. I think it's just like 2 minutes long. If you haven't seen this before, I mean, I can just tell you this. It's just going to tell you what I just told you, but it's really something to see. So I'm just going to share that with you.
Hi, this is Bill Putman. I'm a climate scientist at NASA's Goddard Space Flight Center. What you're looking at is a supercomputer model of carbon dioxide levels in the Earth's atmosphere. The visualization compresses 1 year of data into a few minutes. Carbon dioxide is the most important greenhouse gas affected by human activity. About half of the carbon dioxide emitted from fossil fuel combustion remains in the atmosphere, while the other half is absorbed by natural land and ocean reservoirs. In the Northern Hemisphere, we see the highest concentrations are focused around major emission sources over North America, Europe, and Asia. Notice how the gas doesn't stay in one place. The dispersion of carbon dioxide is controlled by the large-scale weather patterns within the global circulation. During spring and summer in the Northern Hemisphere, plants absorb a substantial amount of carbon dioxide through photosynthesis, thus removing some of the gas from the atmosphere. We see this change in the model as the red and purple colors start to fade.
Down the bottom, we're in June.
Meanwhile, in the Southern Hemisphere, we see the release of another pollutant, carbon monoxide. This is a gas that's both harmful to the environment and to humans. During the summer months, plumes of carbon monoxide stream from fires in Africa, South America, and Australia, contributing to high concentrations in the atmosphere. Notice how these emissions are also transported by winds to other parts of the world. As summer transitions to fall and plant photosynthesis decreases, carbon dioxide begins to accumulate in the atmosphere.
I'm just going to stop there because you get the point. So nature has been doing this for literally millions of years. And I want you to keep that in the back of your mind as you think about different solutions and different ideas that are proposed as cause and solution. So that's not 100 years, not 50 years ago, 100 years ago, even 200 years ago. Ask, what was nature doing for all this time that kept the climate in balance? And that's one of the things that kind of directs how we're thinking, how I think about climate change and climate solutions. Is this something that restores nature to the systems that have worked for so long?
Hi.
So we'll talk about nature-based solutions to 3 different problems. So if you have a solution, you have to have a problem. I tend to think of climate change as a predicament. There's so many intersecting problems. There's not one thread that you can solve for and take out. But so to me, it's helpful to use these terms for their original purpose. So at the very bottom of this pyramid, you have the greenhouse effect, which we just saw. And that's how the emissions are warming up the planet. But then you can use the term global warming, and this is focusing on heat and all the ways that heat is trapped on the planet. And then climate change are the impacts of that, which are mostly extreme weather impacts and health impacts. So these 3 interconnected challenges can be addressed through a living systems approach to climate. So instead of just pulling out one thread, emissions, we can talk about them all together and how they work together. So the greenhouse effect is the one that most people are aware of. And I mean, to be honest with you, this is how the United Nations defines climate change, the same as the greenhouse effect. And so we're going to be looking at how nature sequesters the excess carbon dioxide in the atmosphere. And a few of the key ecosystems that do this are wetlands, oceans, and forests. So I'm going to start with wetlands and inland forests because forests are huge, and I don't know why. Wetlands seem to be the one that people think the least about. So wetlands sequester a lot of carbon. You can see a wetland isn't just a pond. It is full of plants and microbes and all the kinds of things that you think of when you think of a forest as well. So this one study that just came out this year says that New England salt marshes store 10 million cars worth of carbon and another 15,000 worth every year. So, and this is from satellite data. How do they do that? Here's kind of a diagram of all the pieces of the ecosystem in the wetland that are responsible for absorbing carbon. You've got the plants. You've got the little shell animals that are taking up carbon to make their shells. You've got the little microbes in the soil. And they're all working together, absorbing carbon dioxide. And you need a lot of biodiversity to do that, for this ecosystem to work. It's not any one piece of that. And that is why our organization is focused on biodiversity, why we call ourselves Biodiversity for a Livable Climate. Because you'll see time and time again that a healthy ecosystem requires a wide variety of diverse organisms. So here's the problem. Wetlands have been disappearing. Take a look at this map. Hopefully you can see it pretty well. It's tiny, but all the red is where there used to be wetlands and there aren't anymore. And the blue is where there still are wetlands. And the gray is where they don't actually have data. So tiny, teeny, tiny, all of the, you would expect there would have been wetlands here. But what I find very interesting is the west coast of California, which we think of as desert area, but that also used to be covered with wetlands. 3.4 million square kilometers have been lost since the 1700s, which comes out to be 3, 4, 5, or even 6 times more wetlands in the past than we have now. So those missing wetlands are not absorbing carbon, and they're not fulfilling their other ecosystem services that we'll see a little bit more about later. Basically, and it makes a lot of sense, everywhere that there's people, we've filled in the wetlands and built stuff. And you can see that across the map. The solution? Beavers are actually great wetland builders. And beavers can create a wetland in 1 year. We have a YouTube video you can link to about a story that's been going around, actually going around social media right now, how in the Czech Republic, beavers built like a huge acreage of wetlands while the Czech government was still doing the paperwork and bureaucracy to get it done. And we have a lot of examples on our website of eco restoration projects, including ones in California where they brought back beavers. And if you can just find enough of a river for them and the kind of trees they like, they'll come and do the work for you. So a little spoiler alert, wetlands also reduce flooding, create fire breaks, create fire refugia, clean water, support healthy water cycles, and help with the rain cycles. And we'll talk about those a little bit later. We love the beavers. All right, the next ecosystem that sequesters carbon is the ocean systems. You may have heard about whale poop being important because that is what the phytoplankton eat, and phytoplankton are little tiny microscopic plants that absorb carbon, and that boosts the carbon absorption of the whole system. Shells, marine shells, lock away carbon because they're made of calcium carbonate. And seagrass, just like above land, on the land, grass has photosynthesis that absorbs carbon. Grasslands, they're deep root systems take carbon out of the air and take it deep into the ground and store it there, along with the microbes and the fungi that live underground. They all work together to pull that carbon out and store it. A way to increase the ability of these grasslands to absorb carbon is through proper grazing management. And we have quite a few examples and studies where grazing animals have a positive effect on the grasslands by fertilizing it, and by their hooves help keep down grasses, but also they make divots that hold water, so they work in both ways. And of course, they have the biodiversity of the ecosystems. They're great biodiversity sinks. So forest is the heavy hitter. And I hope by the end of these few slides, you'll see how forest ecosystems are so essential for every single one of our climate change problems, for heat, and for sequestration. So right now we're on the carbon sequestration part of the equation. And it's fairly self-evident how forests take in carbon through their trees, through the leaves, and through photosynthesis, store that carbon in the branches, in the roots. It gets down to the ground and is stored below ground. And they do this throughout their lives. You may have heard some studies claiming that it's okay to cut down these forests because new trees, are pulling in carbon more quickly as they grow, which is kind of true, but not as true as you think. They may be pulling them more quickly, but they don't pull in more. And so this has been a little controversial among those of us who study nature-based solutions. And this study that I just pulled up here is fairly recent, October of last year. And you can't tell from the language, land use change, no net loss policies. So net loss is no net loss policy means you cut it down, but you plant the same amount. So they claim you have the same amount of forest. And what they found out is that those do not sequester as much carbon. And I'm going to tell you, they're not healthy forest ecosystems either. And they tend to be monocultures, but even if they were planted correctly, they wouldn't be able to reproduce all the ecosystem services of a healthy biodiverse forest. There's a link to that study, and there's more studies on that. So this is why cutting down trees for pellets, you may have heard of this, cut down a forest, turn it into pellets, use it to create electricity, and grow a new forest, and it's called carbon neutral. No. You have destroyed a forest ecosystem. It will not absorb as much carbon dioxide, and it also won't create all the cooling effects that we'll talk about later. And besides, we just know that's sad. It's just wrong. All right. So that is the carbon dioxide emissions piece of how nature works. The bottom line is photosynthesis, right? Wherever you can increase photosynthesis, you are increasing the ability of nature to pull in carbon. But let's look at warming in itself. And this is looking directly at the heat. How can nature help us bring down the temperature aside from pulling out the carbon? So there's two ways to control heat, right? You can reduce the amount of heat coming in or being reflected, or you can enhance the cooling power. And the nature systems are not unlike human systems, right? When you're overheated, you get out of the sun and your body starts to sweat, to use water to pull heat away from your skin. It works that way with nature. And this is a fabulous animated video that explains it better than a bunch of slides, and I think you're really going to enjoy this.
In a time of rising temperatures and climate instability, most of the attention goes to greenhouse gases. But there is another way, often overlooked, to stabilize the climate and cool the planet: plants. Unlike high-tech geoengineering schemes, forests, wetlands, grasslands, and marine ecosystems bring numerous benefits beyond just cooling the atmosphere. They increase biodiversity, they can prevent floods, and prevent erosion. But for now, let's talk about how they stabilize the weather and promote cooling. We all know that plants drink water through their roots, but what happens to that water? Most of it comes out through the leaves as part of the process of photosynthesis. In fact, for each molecule of carbon dioxide fixed and each molecule of oxygen released, several hundred molecules of water are evaporated. This is what we call transpiration. And it cools the forest in the same way sweat cools the body, the evaporation absorbing the heat. That's why forests feel so cool. It isn't just the shade. On the edge of the Amazon rainforest, temperatures are consistently 5 degrees cooler than on farms just a short walk away. And in Sumatra, native forests have been measured to be 10 degrees cooler than neighboring palm plantations. Leaves aren't just leaves. They're home to many species of bacteria, some of which are light enough to rise high up into the atmosphere along with the transpired water vapor. These bacteria are small, but much larger than the water vapor particles. So the gaseous water vapor uses the surface of the bacteria to condense into liquid droplets, creating clouds much more quickly. Forests, grasslands, and marine ecosystems each produce their own kind of condensation nuclei as well. In this way, plants seed clouds. When the water condenses at cloud level, it releases the heat that it absorbed during evaporation. Therefore, transpiration moves heat from the ground level, where it would have been trapped by greenhouse gases, up to high altitudes, where a lot of it, as much as half according to some experts, radiates back into space. Heat exits the Earth, and the Earth cools down. Now what if for some reason we didn't have the plants here? Well, then we wouldn't have the condensation nuclei, so the water vapor wouldn't be able to form clouds, and would form a haze instead. Then it causes heating, not cooling, because uncondensed water vapor is itself a greenhouse gas. So we know from the previous 2 points that more plants means more clouds, because of the transpiration and the condensation nuclei. While clouds have all kinds of warming and cooling effects depending on various conditions, on average we get a net cooling effect. Overall, more clouds means a cooler atmosphere, because clouds reflect sunlight. Another important feature of clouds is that they make rain. The worst damage from climate change comes not from heat per se, but from floods, droughts, fires, and irregular rainfall. Intact ecosystems help extend the rainy season by absorbing water into the soil, which replenish aquifers and feed springs, which then feed water to plants to keep them green and transpiring. This makes them way more resilient to fire. Healthy soils and wetlands are also like a sponge that mitigates flooding during the rainy season. You know how carbon is a pretty major greenhouse gas? Well, plants are made mostly of carbon. Not only does their growth directly take carbon out of the atmosphere, but lots of it goes underground, taking the form of their roots, as well as carbon-containing compounds the roots exude. This carbon that was once in the atmosphere stays underground, sometimes for hundreds of years if left undisturbed. Grasslands and wetlands are especially good at sequestering carbon and building soil. Finally, let's not forget the 2/3 of the planet covered by water. The ocean food web is, like the terrestrial, based on plants: seaweed, algae, and cyanobacteria. Okay, that one's not technically a plant, but let's just include it. Marine ecosystems contribute to cloud formation, as do land-based ones, and they also sequester massive amounts of carbon in the form of shells, which are made of calcium carbonate. When reefs, estuaries, and kelp forests are healthy, shellfish thrive, and their shells take carbon out of the atmosphere, while also counteracting ocean acidification. Okay, great, let's just plant trees anywhere and everywhere and fix climate change right now. What are we waiting for? Well, be careful. There have been a number of reforestation efforts, and some have ended in disaster. For example, when fast-growing trees suck up the available water and die, leaving the land a desert. That kind of thing often happens when we use carbon calculations to guide ecosystem regeneration. We have to think holistically. A healthy forest is more than a bunch of trees. A palm oil plantation has a lot of trees, but it doesn't make clouds, cool the air, build soil, or prevent drought like a forest does. Not just forests, but all ecosystems are like organs of a living planet. Like your organs, they control the body temperature, direct its fluids, and maintain the life of the whole.
Do you feel like I could take some questions here if people had something on their mind, particularly as this is such a great overview of the things that we've been talking about, and really Jimmy Eisenstein says it better than I could in many ways. So Megan, I don't know if I should stop share just for a minute and see if there's some questions.
Sure, yeah. If you have a question, you can either post it in the chat, or you can use the hand raise tool and then I can unmute you.
I think one of the things that I found most that I thought Jimmy did a very good job with is showing the difference between the palm plantation and the forest. And if you see headlines that say, tree planting didn't work, tree planting is a failure, forests don't regenerate, it's usually because they've not tried to create a forest ecosystem. They're just sticking trees in the ground. One of our scientists, Anastasia Makareva, reminds people that trees are not just carbon sticks. They are part of this ecosystem that transfers water, creates the clouds. All right. Well, I'm going to have you guys are a smart group. So let's go ahead and finish up the presentation and get to the nature-based solutions for the different extreme weather. Go ahead and share. Make sure I got it all set up the way I like it. Great.
In a time of rising
Next slide. All right. So we know forests cool. They have a cooling effect, and that cooling effect comes from the way that they use water. But how much cooler? So there's a great study that came out early last year saying that a century of reforestation in the eastern United States has significantly protected us from rising temperatures. By how much? They say by 9 degrees, up to 9 degrees Fahrenheit. So this is the cooling effect was most pronounced at midday in the summer when we need it most, lowering surface temperatures by up to 9 degrees. Now, if you average that out over the year, it comes out to something like 1.4 degrees overall, but 9 degrees is pretty significant. I'll take a forest in my backyard to help with that. When you understand how the forest ecosystem works, you can keep in your mind that forests are far more valuable than the lumber they produce or even the carbon credits that they produce. It's only an intact, healthy forest ecosystem that's going to do all those things, create the clouds, slow the wind, create rain, hold carbon, and support the soil life and be effective at transpiration. So we have an example of how this works in the urban environment. Our organization has been a leader on the East Coast, then particularly Northeast, in planting tiny urban forests. They're called the Miyawaki forests because they were pioneered by a Japanese scientist, Yukara Miyawaki, about 40 years ago. And they've been quite popular starting in Japan and then spreading throughout Europe. But not quite as popular here in the United States and North America. We are not the first in the country. There are some that you can find, and you may be familiar with some. And I believe right now people are very excited. Ours is in Cambridge, Massachusetts, but I think there's one in Arlington and definitely some in Maryland that have come up since we planted this in 2021. I don't know if you can see, so we partner with Salem State College, and they have a drone that takes thermal images. And so they've been helping get data in the last year on our forest. This is in Danahy Park. It was planted in 2021, so it's about 3 years old, and that's when they become self-sufficient. They You have a special process to work the soil. You plant a wide variety, like 32 different species of plants and trees, very closely together so that they can create that community. And within 3 years, they're pretty self-sufficient. But they do need weeding for those first few years and watering. But after that, they should be fine. So what you see in this thermal image, the question we're asking is how much cooler, right? So because he's doing scientific data and everybody else uses the centigrade, these are in centigrade. You see here in the forest, you've got 23.6 degrees along the edges, and that's pretty consistent towards the middle here, and a few spots. So that's, I think, surprisingly consistent. So right over here, it's 29.9, which is, in centigrade, that's quite a few degrees more. And here in the dirt, it is 51.4, which is actually hotter than the pavement over here. So it's really incredible how, first of all, how hot bare ground is, and why it's important. Even with the grass here, you've got significant cooling compared to the bare ground, but you're finding the most cooling here in our little forest. And we have a whole page on this on our website, and you should definitely look at it, because we have 6 forests now, and it's really astonishing and rewarding to see them come up. So that is the cooling. So we've talked about warming and cooling. Now let's talk about nature-based solutions to climate change effects, which are basically extreme weather events. So we're seeing an increased frequency, increased intensity, and an increased probability, which I didn't write here. And so we're talking about storms, droughts, heat waves, the drought flood cycle, hurricanes, not only increased frequency and intensity, but weather where it doesn't belong. I mean, if you recall the Ashland being hit by a hurricane, this is a mountain community. I mean, the weather's gone a little crazy. And climate is weather patterns over time. So how does nature influence weather? Through the water cycle, through wind patterns, and through regulating temperature. Now, by this point in the presentation, you're already kind of an expert on all those things, because we've talked about them in the context of carbon and in cooling. But let's take a look at fire. So fire's on our mind. The LA fires were so devastating, and at least it made people look at it, right? And there really was a conversation this time about the role that climate change is playing and all the different factors that go into it. So this graphic is a little hard. AI made this graphic for my communications manager, but in here you can see all the different pieces of an ecosystem. They're going to make an ecosystem more resilient to fire. I don't think anybody can claim they're going to prevent fires, but you can lower the probability and make the ecosystem more resilient. So forests are going to slow wind. We know in LA, those Santa Ana winds were so powerful and so fast that they just moved embers right through the community. They retain moisture. We've seen how they generate their own rainfall. They create a soil sponge that keeps when you hold this moisture, so this is a wetland, right? And that's our little beavers help make this wetland. And if we still had those wetlands that we had seen on the map in California, you would have more of this kind of ecosystem that trees can pull from, plants can pull from. All that dry grass had a chance to stay moist and be less, and to be more fire resilient. We've got some grazers over here. When you do have one of the other problems in LA was they had a rainy season last year that was really great. So a lot of grass, I will tell you, it was not native grasses, but a lot of grass, non-native grasses grew, and there was nothing to really take it down. So when you have natural grazers, I used to, as you know, I used to live in Santa Barbara and near that ecosystem. It's a really dry, it doesn't look like this. It's like little dry things. So you're not going to have deer and antelope, but you might have bunnies and other little grazing animals. So that keeps down the fuel load, is the bottom line. So you can create a healthier ecosystem that is more fire resilient. We talked about the role that beavers play in creating wetlands, and those wetlands are really amazing at creating fire breaks and fire refugia. You can see right here, this is after, oh, I can't remember the fire. I think this was a Colorado fire. It's a very specific one. Came through, all of this burnt. All of this burnt. This is the river back here. There's still river back here, burnt. The fire crossed right over. The wetland created by the beavers is intact. So is this a fire break? Obviously, the fire got around this little wetland and went to the other side. So I don't know if you call that a fire breaks per se, but there is staging ground. A lot of fire breaks, need ground where firefighters can set up their equipment and fight the fire on either side. What it really is a fire refugia, because where does the wildlife go during this fire? This is a place where all the animals can come and be safe and survive the fire. So that's the difference between a fire break, is going to stop the fire, and a fire refugia provides refuge for the wild animals. So how do beavers do this? There's a great little animation. Emily Fairfax is a scientist and researcher who's been collecting data on the role that these beaver created wetlands are playing in helping with fire and make more fire resilience. So here's how it works. Oh, there's no music to this one. Oh, there is. Oh. His little flag said, "I'm okay." So he's got his little check in there for you. So you can see basically this, we have a link to this on the fire page on our website, or you can just look it up on YouTube. It gives you a little bit about how these beavers do it. They're just amazing. We love beavers for so many reasons. So the way that we are looking at creating fire breaks now is basically through logging. And I first started to make this a priority for Bio for Climate a couple of years ago when we had fires in Canada. And then last year, I read about a massive fire break they're creating in Banff, a beautiful, pristine area. And because embers can travel up to a mile, and or more, depending on the wind, the fire break has to be a mile wide. And you saw in our picture of how the fire can go around a small break. I don't remember exactly how many miles long, but a mile wide swath, miles long, in the name of stopping fire. And I thought there has to be a better way. Nature has to have a better solution. And that's why we started looking into this, because that is devastating. And you can go to the website, I linked to there. It's an article about how great these fire breaks are, but you can scroll through their photo essay and see the pictures of it for yourself and see how great you think they are. When I was reading about this, it was the municipality was very excited that they didn't have to pay for this, because the timber company was going to cover all the costs for them and take all the sellable wood. And the non-sellable wood was just left there. And I don't know why nobody's asking why that doesn't become fire fuel, to have all that small wood and branches left on the forest floor, on the floor to dry. In a healthy forest, those small branches would be protected and in a moist environment and rot instead of drying out and becoming fuel. But in a big clear cut like this, they're just going to dry out. So, the unintended consequences, the wind is going to whip through there. They made it a mile wide, but a wind like they had in LA with no trees to stop it, and who knows if that'll even be enough. So our preference is to keep the forests as healthy as possible, restore those wetlands, keep the moisture in the forest, and to make more fire resilience. Clearly, if there's no trees in the forest to burn, you won't have a forest fire, but I don't know what you're accomplishing by removing the forest. Though the answer they would give me is you're protecting property. So this, wherever, because there's no forest there to burn, it will not get to cabins and in cities. Talking about fire makes me so sad and clear cutting. But let's go on to extreme weather and floods. So how do you prevent floods? Wetlands are going to absorb and act as natural sponges. The soil, anytime you have healthy soil with infiltration, it's going to absorb in more biomass, it's going to absorb water. And we already know how great forests are at absorbing water. So when you talk about any of these ecosystems, the soil is really important. And if you've watched Kiss the Ground, you've probably got a little primer in how important soil is in agriculture, and it's true for any ecosystem. So Dee Pershouse is a leader in talking about the soil carbon sponge. This was something that was developed. This idea was first noticed by a scientist, Walter Yena, in Australia. They actually first met each other at a Bio for Climate conference about 8 years ago. And you can find that video on our YouTube channel. But anyway, her experiment here shows different, she says these 5 trays of soil, they're all the same type of soil, but they were managed differently. So they're kind of from the same area. And they each soak up different amounts of water and have different amounts of runoff. So you can see by the time you've got this bare soil here on the right, let me get on the pointer here, right? Lots of runoff, lots of water and lots of erosion. You add some biomass, you add some ground cover, you add some microbes, you can put in some plants, and by the time you get here, there's almost no runoff. I have a friend actually who lives in Alexandria and works for the Alexandria Library, Megan, who learned about this, and she asked her landscape crew, like, instead of coming and putting more nitrogen on my lawn, can you increase the biomass or humus? Humus. Humus you eat, humus is in your dirt. And she said it took a while to find someone who would do it, but they did it, and because she had a drainage problem on her property, and she was tired of putting in, let's not do more storm drains or more pipes. Let's see if we can fix this with soil. And it worked. She's just like, we're all amazed. Like, yeah, she improved the soil, improved the soil biomass, and this gully that used to run off her yard is no longer a problem. So this is not just a solution for governments, it's a solution for anyone. All right. So when you apply all these solutions together in an urban environment, the nickname is sponge cities, right? So you put in as much greenery and as much water retention as you can. So green roofs, rain gardens, permeable surfaces. And if you Google sponge cities, you're going to find some real fun examples. I believe Singapore is one of the ones that'll come up. But I was also surprised to see, I believe it was Philadelphia is trying to become a sponge city. And we work with an urban planner on our Milwaukee Forest program. And I was looking at their website, and urban planners are planning these kinds of things into new development. So you may not hear about it because they're not a nonprofit who's talking a lot about it, but people are waking up to how important this is. All right. Forests, as we are not surprised, also help protect against floods. I left them for last because they're just so important. So the canopy, the leaves themselves, block raindrops as they come down. So they're not hitting the bare ground. They're going to gently fall to the ground where they can be absorbed into the soil. The root systems create those channels that bring water down deeper into the soil and prevent erosion. And they filter the debris, right? Whatever's, if you get a lot of water, a rainwater event, they're going to stop some of the leaves and whatnot flowing downhill. So with trees, without trees, you can see the dirt coming down in, you can see a much wider problem. Not to say there is some flooding next to forests, but not to the extent from deforested forests. I was really surprised when we heard about ashland. You look, I don't know if you've ever, I've met a lot of people from ashland, and they're very cool, and they're very into nature and ecosystems. And it's a beautiful area surrounded by trees. And I'm like, how could they have had so much flooding? When you zoom out to the aerial map, there's been a lot of mining behind those trees, which in order to do mining and mountaintop removal mining, you have to get rid of all the trees. If you ever look at the aerial map, you're driving along the highway and you think you're driving through a forest, and like 10 or 20 feet past that forest, it's all been cleared for whatever's there, right? Next time you're in an airplane, take a look. It's astonishing. So I think this theory stands. I'm always testing these theories against the real world. We're very interested at Bio4Climate in not what the models say, not what some computer program says, but what's happening in the real world. So I think that really proved true in Ashland as well. All right. The other problem is drought. So climate change is causing flooding and droughts. It seems like that shouldn't be true, right? It should be one or the other, but it's doing both. So we know that, how do you address that? So we know trees are rainmakers through transpiration, cloud seeding, microclimate, just what Jimmy Soul talked about in his video. So you need more trees. Now there's another function that forests serve. It's called the biotic pump, and it is how forests move rain inland. We could go into some detail about the small water cycle, the large water cycle, but basically, you can see there's a low pressure area is created here, which gives the hot air a chance to rise. And as it does that, then it comes back through here and moves these clouds inland. Without that, you see here, there's no forest, no trees. The water cycle just kind of happens here. The water evaporates, goes up, comes back down, evaporates, goes back up, and has to rely on, I mean, there are wind patterns that will move that through, but this creates an inland, regardless of where the wind is blowing, brings that water inland. So another reason to have intact forests. What happens when this part of the forest here is logged with a mile-wide fire break? You're likely to have less rain on the other side. So we want to do that. All right. That's not by far all the nature-based solutions. Every ecosystem is a solution, and there's a lot more you could talk about. Bio4Climate offers 12-week courses on many of these things. We also have some shorter courses. We have a series of videos. Even though you didn't have any questions after Jimmy's talk, we talk about each one of these things for hours every week at our team meetings and whatnot. So let's just skip through. Given those key things that we've talked about, one of the things I promised you at the beginning was that you have more agency over nature-based solutions than you might have over COP, solutions that require every country in the world to collaborate, right? So what can you do? Restore nature, cool the planet. We talked about planting. Increase the plant cover everywhere you are. Look at your yard, but I noticed over at Sherwood Library, the sod there has worn away and it's just dirt. Great project for your Cub Scout group. Come in and put in some native plants there, restore that soil, and it's going to be soaking up water, soaking up carbon, and in solving the problem. Hydrate, this is a tough graphic because these are not separate things. As we've seen, all these things work together. How do you hydrate? With more plants, with more wetlands. And cool, this block is actually talking about the built environment, which we did not talk about a lot, but in the built environment, when you don't have a sponge city, we've designed our water management so that all water goes down the drain, through concrete pipes, out to a river, out to the ocean. It never has a chance to get to the soil. So that's creating a lot of heat in itself. And those surfaces themselves, we saw in the picture of the Miyawaki forest, bare ground and paved surfaces are radiating more heat back out than the ones covered with plants. So that's more heat to be trapped in the greenhouse layer than we'd have otherwise. This last one is a catch-all. Protect what you can, right? These are active things we can add, but when we saw that study about old growth forests, there's nothing that beats a mature existing ecosystem. This is also where we put in a little catch-all to pay attention to indigenous leadership and their wisdom, stop deforestation, industrial ag, mining. All these things are not only bad on their own, but they're destroying the cooling power of nature's systems. Eco-restoration works. This is a little short clip where Tom Garreau is talking about, I'm not going to play it for you because we're close to time here. He's a scientist we worked with early on. This is from one of our maybe 2017 conferences. And he talks about in Rio de Janeiro, about 150 years ago, maybe 200 years ago, they had completely deforested the area. And it dried up and stopped raining. And they knew it. They didn't need a computer model. They're like, oh, this is bad. So using, unfortunately, mostly slave labor, they replanted it with native plants from, surrounding areas that hadn't been destroyed. You look at that today and you think that is a rainforest that's always been there. And it's not true. And he shows you some examples about that. And there's many more examples like that from around the world. So we have been, sometimes people say to me, sometimes when I read comments and there's trolls on climate sites, they say, come on, humans can't control the weather. We can't even predict if it's going to rain next week. And it's true, we don't control the weather, but we influence it. And we influence the climate. And so that's the difference. I can't tell it, make it rain on Tuesday, but I can create an ecosystem where there's going to be more rain overall. And humans have known this for a long time.
Sorry.
So now what? Now that you have this background, and I hope I've given you enough of a taste of it, that you see what the living systems, you put this all together and we call it the living systems approach. It's not just technology or linear inputs, in more carbon and out less this. It's creating living systems that regulate climate and all the different aspects. For me, I ask, does this solution restore nature's functions? Does it bring the ecosystem back to the way it was when it was fully functioning? So that's what I ask. And then act, heal the land where you are, and through support of eco-restoration around the world. Your support of really reforestation in Africa or the Amazon is actually really important. And I know people don't have a lot of extra money right now, but even with policy or educating yourself, all these ecosystems need to be restored. We talk about, I've shared with you things that are mostly US based and mostly things close to home, but there are literally hundreds of millions of hectares of degraded land that need to be restored to bring us back to full functioning. So apply the living systems approach to climate activism. Apply the living systems approach to your life. Believe that you and all of humanity can be a positive part of the web of life. There are so many places we can intervene to help these systems to work and to be a positive part of those systems. And then learn. Join a community of curious and active people through classes and activities. And where would that community be? Well, we certainly have that at Bio for Climate. So however you're going to learn, you can go to our website. This is a clip from our website. We have, here's a couple of classes. Unfortunately, this class here, Journey of an Apprentice, happened right tonight at the same time. This was someone who took one of our classes and he wanted a visual of it. And he said, "Oh, I can't really draw." And Jim, our instructor, said, "Well, just give it a go." So he has all these little stick people. They have these little names, and he goes through all these different ecosystem functions, actually in more depth than we did here. Really delightful. And then we do a series of talks with the GBH Forum Network. This one was about the Arctic. We had the author of a recent book where he had gone to the Arctic in his 20s, and now, like 20 years later, was sharing his experience. Anyway, there's a lot of classes and things you can do. Remember that Earth repair is climate action. A lot of times these are separated out. Oh, we have to protect biodiversity as a separate issue. I hope you can see that biodiversity is necessary as part of the way we deal with climate change. It's not just how absolutely tragic it is that we're losing so many species in the 6th great extinction, but we need this biodiversity of species in each ecosystem to make them work. And whatever you call it, there's a list of ways to call it. My favorite one is rewilding, actually, but it's important. Thank you so much for your time. I hope you learned a lot and that you're inspired to learn more.